In this video, I will discuss JEE Advanced PYQ from the topic Force on a current kinetic conductor due to a magnetic field and Faraday's law of electromagnetic induction. First, some basics. Consider this current carrying conductor Ci and there is a magnetic field in this direction B. The force on this conductor is given as I L B. If L is the length of this conductor, this comes from force on a current element is IDL cross B, and this comes from Lorentz force on a moving charge is Q V cross B. This is Lorentz force. So inside the conductor there are a lot of electrons moving and each electron will have a force. So if we sum all those forces, we will get this one. This was small length element. So for this entire length it will be ILB. And here in this particular case, the current and the magnetic field are perpendicular to each other. So dl cross B will become dl into B into sine theta, where theta is 90 degrees. So it will just become ILB. Another basic thing that's used is, here there is a rail on which there is a conductor which is free to move, and there is magnetic field. Everywhere, uniform. So now, as this rail moves, there will be a current flowing in this closed loop because the flux linking the circuit is changing in time. So this is the induced EMF according to Faraday's law of electromagnetic induction. And this flux can be written as the magnetic field B into the area of this loop divided by dt. So B is uniform and constant, so it will come out. And then A is, this length is L and this length is, it's a variable length. Let me call it Y. So L is also constant, so L also will come out. And then dy by dt, which is basically the velocity of this rod. So it will be VLV. So with this basic ideas, you can solve this JEE Advanced question. This is the question, you can read it. A thin conducting rod Mn of mass 20 gram, length 25 centimeter, and resistance 10 ohms is held on a frictionless, long, perfectly conducting vertical rails as shown in the figure. There is a uniform magnetic field B0, 4 Tesla, directed perpendicular to the plane of rod rail arrangement. The rod is released from rest at t equal to 0 and it moves down along the rails. Assume air drag is negligible. Match each quantity in list 1 with an appropriate value from list 2 and choose the correct option. Given the acceleration due to gravity g is 10 meter per second square and e raised to the minus 1 is 0.4. List 1, P at t equal to 0.2 seconds, magnitude of induced EMF in volt. Q at t equal to 0.2, magnitude of magnetic force in Newton is. R at t equal to 0.2, the power dissipated as heat in watt. S, the magnitude of terminal velocity of the rod in meter per second. List 2 has got some values, so to match these two. 4 options are given. You can pause and run this question. The force acting on this rod, it's a vertical rod, vertical rails, is the weight mg downwards, g is downwards, and when the thing is moving, there will be a induced EMF in this closed, so there will be a current flowing here. The current will flow in a direction such that the magnetic force This is the upward direction. This can be got by Lenz's law. Lenz's law states that the induced EMF will be in such a direction that it resists the change. So as it moves down, the flux linking this closed path will increase. So it will try to reduce the rate at which it's increasing. So it will try to exert a force upwards so that it does not fall quickly down. So the net force acting on the rod is mg minus magnetic force in the downward direction. So the net force is mg minus magnetic force, which is ILB. Which comes from ideal cos B, and the angle between I and B is 90 degrees, and over the entire length ILB, and that basically comes from the Lorentz force. And induced EMF d phi by dt, which is BL into V. The V is the velocity of the rod which is falling down. And the current is induced EMF by R. So I is this induced EMF B, L, V by R. So now the BL is here. And the net force is mass into acceleration. So m into dV by dt. So this will become dV by dt equal to G minus B square L square V by R M. M is getting divided throughout. So now, using the given values of B, L, and R and M, so this will become B square is 4 square, length is 25 centimeter, which is 1/4 of meter. So 1 by 4 square is L square, and R is 10 ohms, and mass is 20 grams, which is 20 by K kilograms. So this is K by 200, which is 5. So from this I'll get dV by G minus 5V equal to dt. dt take on the other side, and this thing is G minus 5 into V, bring it down. Now integrate this thing both the sides between the limits t equal to 0 to some arbitrary time, and when t equal to 0 it starts from this, so velocity is 0 to the velocity at time t. So this is logarithm divided with the derivative of this thing, that is minus 5, and we have to put the limits 0 to V. This is just t. So minus 5 can take it there. So this will become log of this one minus log of this one. So log A minus log B is log of A by B. So this will become ln G minus 5V. When you put the upper limit, when you put the lower limit, become G. That's equal to minus 5T. So this will become 1 minus 5V by G equal to E raised to the power minus 5T. This is log to the base E. So this will become this one. So from this I'll get velocity as 1 minus E raised to the power minus 5T, and this is actually 2. G is 10. So this is the expression for velocity. So if you put the time, different values of time, you get the different values of velocity. So option S, or the list 1, the S says terminal velocity of the rod is terminal velocity is the velocity at time t equal to infinity. So from this I'll get velocity at t equal to infinity as this thing will go. It is 2 SI units meter per second. So that is 5. So S will match with 5. So you get one match. S and 5 will match. Magnitude of induced EMF. Induced EMF is BL V. We have to find the velocity at time 0.2 seconds. So from here I can get the velocity at point anytime. So velocity at 0.2 seconds, we call it V1 equal to 1 minus e raised to the minus 5 into 0.2 into 2. 5 into 0.2. So this is 1 minus e raised to the minus 1. E raised to the minus 1 is given as 0.4. So it's 0.6 into 2. So 1.2 meter per second is the velocity at this time instant 1, which is 0.2 seconds. So using that, I can get the EMF at the instant 1, which is 0.2 seconds, as B is 4, L is 1 by 4, and then V is 1.2. So it's 1.2 volts. It's the induced EMF at time 0.2 seconds. So induced EMF is 1.2 volts. So 3. So Q3. So I got another match. Q1 3. Sorry, P and 3. P is the induced voltage. Q is magnetic force, that is ILB. Magnetic force at instant 1 is ILB. So I at instant 1, which is the induced EMF by the resistance. Induced EMF is 1.2 volts and the resistance is 10. Length is 1 by 4 and B is 4. So it's 0.12 Newton is the force at t equal to 0.2 seconds. So magnetic force is 0.12 Newton. So 4. So R will match with magnetic force Q. So Q4. Power dissipated as heat at 0.2 seconds. So it's I square R I at time instant 1 into R. So I1 is this one 0.12 into R is 10. 12 square is 144 and then 10 raised to minus 4 from here. So it will become 10 raised to minus 3, which is 0.144 watts. So option 2, R2. So R2 is a match. So P3 and then Q4. So it's option D, R2. So option D is the correct option. D is the correct answer. So this is what I explained here. The net downward force on that rod is the weight downwards minus the upward magnetic force is BIL. And inertium is d phi by dt. Flux linking the thing is B into A, and A is L into Y. B and L are constantly come out. So only Y is there inside, and d by dt is nothing the velocity of the rod. So the net force mass and acceleration is similar dv by dt equal to mg minus B. I is this induced EMF by resistance. So BLV by R and then L. So this will become dV by M divided throughout. So dV by G minus B square L square by Rm into V equal to dt. So integrate between the limits 0 to t, and the velocity at t equal to 0 is rest, so it's 0, and the velocity at any time is v. So this ln, you have to put the limit 0 to v. So you'll get this expression for the velocity as a function of time as 1 minus e to the minus 5t equal to v by 2. Because this quantity, if you do the calculation, it will become 1 by 5. Because b is 4 and L is 1 by 4, 25 centimeter, 1 by 4 meter. So BL is actually 1. So just R into M. R is 10 and mass is 20 by K. So this is 200 by 1000, so 1 by 5. At t equal to 0.2 seconds, the velocity V1. V1 stands for the time instant, 0.2 seconds. So from there I get the V1 as 1.2 meter per second. Induced EMF is BLV. At instant 1 it is V1, so it will be 1.2 volts. So option P and 3 as a match. Magnetic force is BIL. B is 4. I is this induced EMF by the resistance 10. Length is 1 by 4 meter. So 0.12 Newton. So Q and 4 will match. Power dissipated is the ohmic heating. I square R at the instant 1. So it's I1 square R. And I1 is 1.2 by 10. This quantity. So it's 144 into 12 square is 144. So 10 to the minus 4 will come from here. So it will become 10 to the minus 3. 0.144 Newton watts. So it's R and 2 is a match. Terminal velocity at the time infinity. So in the velocity expression, put t equal to infinity. So this term will go. So v equal to 2. So correct option D.